Greetings everyone, and welcome to the Toy Car Post Lab. So in this lab, we measured the distance the toy car moved as a function of time. Right? We picked times like every 3 seconds and we figured out how far the car went. And we then graphed distance versus time, distance in centimeters and time in seconds, and we got, of course, a nice linear graph. And not only was the graph linear, as evidenced by your very high correlation, but it also went through 0, 0. So as we've seen in a couple of other labs, when two variables result in a linear graph that goes through 0, 0, those two variables are proportional to one another. So we can say that the distance is proportional to the time, or even directly proportional to the time. So if we let the car run for twice as long, it'll go twice as far. If we let it run 3 times as long, it'll go 3 times as far. Now that's a powerful thing to know. It tells us there's definitely a relationship between distance and time for the toy car. But we can be a little more specific if we go into a math model, which we can make because we have a linear graph. So we can use our old friend y equals mx plus b. The y here is our vertical variable, which is the distance, which I'm going to call d, and that equals your slope. Now, unlike with the circle labs that we've done, the slope here is going to be different depending on your car. It'll depend on the batteries. It'll depend on where your knob exactly was set on your car. So I'm just going to put in a number symbol here. You might want to put in your slope. The units for that, though, will help us understand what it means, even if we're just thinking of it as a generic number. Units for slope come from the same place slope comes from, rise over run. So our units of rise are centimeters, and our units of run are seconds. So we have some number of centimeters per second. Now, think about what that would mean. This is a graph of distance versus time. How much distance for a certain amount of time. So what does this slope mean? It means that your car is going that many centimeters every second that goes by. Notice you might have taken your measurements every 3 seconds, every 2 seconds, every 4 seconds, but the slope is just per second, each second, or every second. Now, that's something we're going to generalize in just a minute here, because that's kind of an important idea here, how far something goes every second. Just to finish up the math model, the x variable is the time, which we would call t, and your y-intercept is essentially 0. You can check it with the 5% rule, but it should be really small, which means in this case, when the time is 0, the position is 0. And certainly, that should be true. I mean, after all, we started the timer, right when the car got to the 0 centimeter mark. So it hadn't gone anywhere yet when we started the timer. So that means there is our specific math model. Now, one of the big things to get out of this lab isn't just this math model, but it's what the slope actually means and what it actually tells you. So think about what this slope tells you, or what you could call that quantity, how many centimeters you go every second. Maybe put it into some units that might be more familiar. It's distance units instead of centimeters, maybe miles. Instead of seconds, maybe hours. So we're talking about how many miles per hour the car is going. Well, there's a couple different words we could use for that. In physics, we use the word speed. Speed will be denoted with a lowercase v, not an s. S is used for seconds. So v is speed. And we can define it operationally to be the slope of a graph of distance versus time. So forevermore, when you see a graph of distance versus time, you know that the slope tells you the speed. Generically, this is how fast you're moving, how many centimeters you go every second, how many hours or miles you're moving every hour. Right? So it's always telling you how far you're going every unit of time. Now, if we plug that back into our math model, we can make a more general math model for this motion. Again, the y is the distance. The slope we now know is the speed, which is a v. And the x is the time. And there is no y-intercept. So there's our math model. Distance is speed times time. Or you might know this more familiar as speed is distance over time, right? Distance divided by time. But either way, this is an equation for this motion. And this is a very special kind of motion. We said originally in the pre-lab that the cars went in a straight line, so this is only one-dimensional motion. But even there it's special, because notice the slope of this graph. It's a linear graph. And since it's linear, that means the slope is constant. And if the slope is the speed, that means the speed is constant. So this isn't just any kind of motion. This is the equation, the math model, for one-dimensional constant speed motion. Right? That's our math model we're looking at here. That's our physical model that we're examining at this point. One-dimensional constant speed motion. And we now have a wonderful looking graph that we can interpret, and we have a math model we can use to make the prediction. Remember, please, when writing up this lab, that everything that is in this post lab, everything on this screen, everything on the previous screen, in one way or another, ends up in your post lab. Thank you, and I hope you enjoyed the post lab.